Welcome everyone. I am S. Venkatesh, Assistant Professor in Department of Computer Science and Engineering from JJ College of Engineering and Technology, Tiruchirappalli, Tamil Nadu. I am going to present a video lecture on the subject CCS 334 Big Data Analytics. Third unit is MapReduce applications. The topic is failures in classic MapReduce and YARN. So here we are going to cover MapReduce, YARN, then failures in classic MapReduce and YARN with conclusion. So big data frameworks, they are designed to handle massive volumes of data efficiently. Hadoop is a prominent open source framework. It has two components, MapReduce and YARN, that is yet another resource negotiator. These systems are built to execute distributed computing tasks over large clusters. Like any distributed system, they are vulnerable to various types of failures that impact performance, reliability and scalability. So if you understand these failures, then it will be essential for building a fault tolerant and high performance big data applications. MapReduce. So MapReduce is a programming model for processing large data sets in a distributed environment. It divides the job into two main tasks. First one is map phase. Map phase means it processes input data and converts it into intermediate key value pairs. Second one is reduce phase. It aggregates and processes the intermediate data to produce final output. The classic MapReduce framework uses a job tracker, which is a master, and task trackers, which are slaves for job coordinations and task execution. Next one is YARN. YARN is a resource management and job scheduling system. It is introduced in Hadoop 2.x. It decouples resource management from the processing model. So YARN includes RM, that is resource manager, which is a global resource manager for the cluster. The node manager NM, it runs on each node and manages containers. Then AM, application master, it manages the life cycle of a single application. Then containers, it executes environments for tasks. Next, failures in classic MapReduce. Job tracker failures. Centralized component, that is centralized job tracker handles job scheduling and resource tracking. It is a single point of failure. Suppose it crashes means all running jobs are lost. No built-in high availability in early versions. Second one is task tracker failures. It is responsible for executing tasks on nodes. On failure, job tracker reschedules the task to other nodes. It leads to performance overhead and recomputation. Then resource underutilization. So fixed MapReduce slots. So for that underuse the CPU. Next one is task failures. So what are the causes for task failures means? Failures means data corruption. Data may be corrupted. Memory may be having a problem, memory issues. Then code bugs, errors in code. Then speculative execution failures. Slow tasks, that is stragglers, are redundantly re-executed to improve performance. It may lead to duplicate outputs, wasted resources, and inaccurate speculation due to shared hardware bottlenecks. So the straggler tasks are executed again and again redundantly. Then data locality failures. Tasks perform better when they run on nodes with the data locality. Job tracker, it may schedule tasks to remote nodes if local nodes are busy, increasing the network overhead. Then checkpointing and recovery delays. Limited support for periodic checkpoints. Recovery from failure, it may require rerunning the entire job or stages. No intermediate progress, saving the unless explicitly managed. Next, failures in YARN. Now we will see what are the failures in YARN. First one is resource manager failures. Central component managing resources and job scheduling. The failure may lead to loss of cluster resource visibility and job scheduling. High availability mechanisms are required for production systems. Second one is node manager failures. It manages containers and monitors resource usage. Failure may cause running containers on the node to be lost. RM reassigns tasks to other nodes, impacting job progress. Application master failures. Application master controls the life cycle of an application. On failure, Yarn restarts it. But some intermediate progress and context might be lost. Then container failures. Containers are isolated environments for executing tasks. Can fail due to resource limits, crashes or the corrupted input. Yarn detects and reschedules them, but if there are repeated failures means it will slow down the execution. Task failures. So it is similar to MapReduce. Task can fail due to code errors, bad input, network issues. Retries are limited. Excessive failures may cause job abortion. Network partitions and heartbeat timeouts. Heartbeats from NM to RM or from AM to RM maintain liveliness. Loss of connectivity. It can falsely mark nodes or jobs as failed. It causes unnecessary rescheduling and task duplication. Resource starvation. Multiple applications may compete for limited resources. Some jobs may be delayed or starved if resource fairness is not enforced. Log aggregation and metadata failures. Logs are needed for debugging failures. Issues in log aggregation, it may lead to missing execution traces, incomplete error diagnostics. Metadata correction can impact job tracking as well as audit trails. Conclusion. Both classic MapReduce and Yarn face various failure scenarios due to the distributed and complex nature of big data processing. While MapReduce centralized architecture introduces limited fault tolerance, Yarn can improve scalability and modularity, but it brings its own set of challenges, especially around multi-component coordination and recovery. Understanding and handling these failures is crucial for building robust fault-tolerant big data applications. Effective solutions include implementing high availability, dynamic resource scheduling, retry policies, and checkpoint mechanisms. So, to enhance system resilience and ensure smooth job execution, this is necessary in production environments. Fourth unit is basics of Hadoop. In that, the important topic is architecture of HDFS, that is Hadoop Distributed File System. Here we are going to have an introduction about Hadoop, then HDFS architecture, what is in the name node, its responsibilities, data node, its functions, FS image, edit logs, secondary name node, conclusion. First one is introduction to Hadoop. Hadoop is an open source framework. It is developed by Apache Software Foundation. This is used to distribute storage and processing of large-scale data sets across clusters of commodity hardware. It is based on a simple programming model that is called a MapReduce and a distributed file system that is called a HDFS. Hadoop enables scalable and fault-tolerant storage and computing. It splits large data sets into smaller blocks, then distributes them across multiple nodes in a cluster. HDFS it forms the foundational storage layer of the Hadoop ecosystem. It splits large data. So it is reliable storage for large data volumes. Then to stream those data to use applications at high bandwidth. It follows a master-slave architecture. There are two types of nodes. First one is name node, second one is data node. The files in HDFS we are splitting it into blocks. It may be 128 MB or 256 MB in size. They are distributed across various data nodes for parallel processing and fault tolerance. Here we have the diagram of STFS architecture. So here we have rack 1, rack 2. In rack 1, the client can read the data and the client can write. In rack 2, we have blocks of data and client can write the data nodes. Then apart from data nodes, we have name node. So metadata operations are done. Then this name node is connected to metadata. Metadata means data about data, which contains name, replicas and file path. So replication is done here. Now we'll see what is name node. Name node means it is the central metadata server in STFS architecture. It manages the file system namespace. It maintains the directory tree of all files. It tracks the metadata of file blocks, including locations and data nodes, but it does not store the actual data or the data blocks. The name node, it keeps critical metadata in memory. It is used for fast accessing while also persisting this information in disk-based structures like FS image and edit logs. Then responsibilities of name node: managing file system namespace. It handles file creation, file deletion, then duplicating, that is replication, then mapping the file blocks to data nodes, managing access permissions, and single point of failure. So it can be indicated by using backups and HA setups, that is high availability configurations. Can be supplemented with backup and checkpoint mechanisms such as secondary name node and newer high availability configurations. Then data node and its functions. Data node is responsible for storing the actual data blocks. Each data node in the cluster sends heartbeat signal and a block report to the name node to confirm its availability. It provides information about blocks it holds. We will see functions of data nodes. Stores and retrieves data blocks upon instruction from clients or the name node. It records list of blocks. It stores to the name node regularly. It performs block replication and deletion as instructed by the name node. Data nodes are designed to operate on commodity hardware and are expected to fail occasionally. STF is designed to handle such failures through replication of blocks across multiple data nodes. Then FS image and edit logs. So FS image, it is a snapshot of the entire file system metadata at a particular point in time. It includes directory structure, file to block mappings, access permissions and other metadata. Edit logs. These logs record every change made to the file system metadata after the most recent FS image was saved. Every file creation, deletion or block replication update is logged sequentially in the edit logs. During startup, the name node reads the FS image and it applies the changes recorded in the edit logs. This is used to reconstruct the latest state of the file system. Over time, the edit logs can grow significantly in size, slowing down the recovery. To address this issue, a checkpointing process is employed. Now, role of secondary name node. So it is not a real-time backup. It does not serve client requests. Instead, it assists the primary name node by performing periodic checkpoints to match the FS image and edit logs. This process helps in reducing the size of edit logs and enhances the efficiency of metadata recovery during name node restarts. Now we will see the working steps in secondary name node. It downloads the current FS image and edit logs from the name node. It applies all changes from the edit logs to the FS image to create a new checkpoint. It uploads the new merged FS image back to the name node. The name node replaces the old FS image and discards the edit logs. High availability in newer Hadoop versions. This process ensures that the metadata remains compact and the name node can restart faster in case of failure. However, the secondary name node operates on a schedule and it does not provide high availability or real-time failover capabilities. For improved fault tolerance, newer Hadoop versions support name node high availability using multiple active and standby name nodes coordinated by a zookeeper based quorum. Conclusion: the HDFS architecture offers scalable, fault tolerant and high throughput access to data with a clearly defined master slave model. It efficiently can separate the metadata management and data storage through the name nodes and data nodes. The use of FS image and edit logs ensures persistent metadata storage. The secondary name node supports checkpointing for better recovery performance. So these design elements make HDFS as a better solution for handling massive data sets in modern data intensive applications. Unit 5 is Hadoop related tools. The topic is HBase, its architecture, features and applications. So we will cover about introduction to HBase, its architecture, what are the key features and real-time applications with conclusion. Introduction to HBase. HBase is an open source distributed non-relational database. It is modeled after Google's Bigtable and developed as a part of Apache Software Foundation's Hadoop project. It is designed to store large volumes of sparse data in a fault tolerant and in a scalable manner. It is built on top of HDFS. It provides real-time read-write access to large datasets and it supports horizontal scalability. Unlike the usual traditional RDBMS, HBase does not follow a strict schema. It is column-oriented. It is well suited for semi-structured or unstructured data. It ensures strong consistency for read and write operations and is optimized for handling large-scale data with high throughput. Now we will see the architecture of HBase. Here we have the client, then HMaster. So client acts as the interface for interacting with HBase. Then region server, it handles read and write requests for the regions it goes. Then region means it represents a subset of the table's data. HMaster, it manages region servers and coordinates load balancing and schema operations. Then Zookeeper, it maintains the configuration information and provides distributed coordination. Then HDFS, that is Hadoop Distributed File System, it stores the actual data files, H files, and WALs persistently. Then you have the Apache HBase. All these components interconnect to each other. So it is a scalable and distributed data model. Multiple coordinator components, that is region, client, HMaster, region server, Zookeeper and HDFS are used. So the main aim is to be a fault tolerant system with high availability. Client. So client acts as the interface for interacting with HBase. It communicates with the HMaster and Zookeeper for locating the regions. It reads and writes data by contacting region servers directly after region location is resolved. Now what is region server? It handles read and write requests. Each region server manages multiple regions. It stores data in H files on HDFS and logs changes in WAL, that is write ahead logs. Then region. So it represents a subset of tables data. Data within a region is sorted lexicographically by row key. Each region contains a mem store, that is in-memory write cache, H files, that is actual storage, and WAL. Then H master. So it is used to manage region servers. It coordinates load balancing and schema operations. It assigns regions to region servers and handles region server failures. It performs administrative operations like creating, deleting and modifying tables. Then Zookeeper, distributor coordination and configuration manager. It maintains configuration information. It provides distributor coordination. It keeps track of HMaster availability and region server health. It facilitates failure recovery and session management. Then Hadoop Distributed File System HDFS. This is used to store the actual data files on H files and the WALs persistently. It ensures redundancy and high availability through data replication. It allows HBase to leverage Hadoop scalability and fault tolerance. Then key features of HBase: column-oriented storage. It stores data by columns, not rows. Then built on HDFS, it uses Hadoop Distributed File System for storage. Then NoSQL and schemaless and non-relational. Then it supports real-time read-write. It enables low latency access to data. Then horizontal scalability, that is easily scales by adding more nodes. Then automatic data sharding, data is automatically split into across the regions. Then strong consistency, guarantees immediate consistency for reads and writes. Distributed architecture or design consists of HMaster and region servers. Then version data storage stores multiple versions of a cell. Efficient compression, that is it supports built-in compression for columns. Then data replication enables replication across clusters. High availability, Zookeeper coordinates failover and monitoring. Flexible data model supports dynamic addition of column families. Integration with Hadoop tools works well with MapReduce, Hive, Pig and Spark. WAL, that is write ahead logging, ensures durability of writes before storage. Bloom filters optimizes read performance using probabilistic filters. Then support for sparse data, efficient storage for tables with many empty cells. Co-processors allow server-side logic similar to triggers. REST and Thrift APIs accessible through web services and client APIs. Backup and snapshot support. It supports data backup and point-in-time snapshots. In applications of HBase, first one is social media activity analysis. It stores and analyzes user activity and timelines. Fraud detection systems tracks transaction history for anomalies in real time. IoT data storage handles continuous sensor data from smart devices. Time series data analysis stores logs and matrices with timestamp indexing. Recommendation engines stores user preferences and product interactions. Search engines supports inverted indexes and document metadata. Clickstream analysis processes web click data for user behavior insights. Telecommunication billing system, it stores call detail records, that is CDRs at scale. Geolocation services tracking manages real-time location data of users or vehicles. Ad targeting platforms, it manages user profiles, campaign data and response rates. Log data storage, it stores and retrieves server logs efficiently. E-commerce platforms, it manages product catalogs, orders and inventory. Healthcare record management, it handles patient history and medical events. Banking and financial transactions, it stores real-time transaction logs and account changes. Then supply chain and logistics monitoring, it tracks goods across distributed systems. Genomics and bioinformatics data storage, it stores DNA sequence data and large-scale estimates. Then CDN, that is content delivery network log and cache tracking, it tracks user interactions and cache data. Then CRM, customer relationship management, systems for customer history. It stores customer interactions, ticket and history. Online gaming. It manages player state, leaderboards and session data. Email and messaging services with metadata management. It stores large volumes of message, metadata and delivery status. Conclusion. So it offers scalable, that is you can extend, and fault tolerant storage for massive, that is large sparse data sets. It is built on STFS. It supports real-time read operation and write operation. Horizontal scaling, already we have seen offers scalable, so horizontal scaling is possible. So the HPS architecture ensures high availability. It is available at any time. For that we are using region servers, HMaster and Zookeeper. So we are having features like versioning, then compression techniques, then co-processors. So it is used for flexibility and high performance. We can use it in domains like IoT, then analytics, then finance, business, then recommendation systems. So we have seen 5 important topics in the subject Big Data Analytics. Hope you understand very well. If you have any query, kindly give your feedback at venkatesh@jjset.ac.in. Thank you.